This video covers the Dense Wavelength Division Multiplexer, or DWDM MUX, and Demultiplexer, or DMUX. We will explore how the behavior of prisms to split and combine light is analogous to the DWDM principle. We'll also cover the technology foundation and various components, including diffraction gratings. Continuing our overview, we will look at specific technologies used in DWDM, such as fiber Bragg gratings, thin film filters, and arrayed waveguide gratings. Finally, we'll discuss the common functional ports and key features of DWDM MUX devices. Prisms split and combine light using the principle of dispersion. A single beam of white light separates into its constituent colors as it passes through the medium. This happens because different wavelengths, or colors of light, travel at different speeds and refract at different angles. This diagram illustrates how white light, when passing through a glass prism, is dispersed into a spectrum of colors, from red to violet. The prism principle is reversible. Multiple discrete wavelengths, such as individual laser channels, can enter a prism from different angles. The prism then combines them into a single multi-wavelength beam. Here we see the reversibility in action. The light is first dispersed by one prism and then combined back into white light by a second, inverted prism, illustrating the dual function of splitting and combining. The prism principle applies to DWDM. A DWDM demultiplexer uses dispersion and refraction to separate a composite light beam into its individual constituent wavelengths, similar to how a prism splits white light into a rainbow. Wavelength separation occurs because the refractive index of the medium changes with wavelength. Different signals are refracted at different angles, which isolates them and sends them to specific receivers. The reversibility principle is also key to multiplexing. A prism-like device can combine multiple discrete laser sources, each carrying its own data, into a single high-capacity beam for transmission. The DWDM multiplexer combines multiple optical signals of different wavelengths into a single fiber stream. Its foundation uses passive filters, such as thin film filters or arrayed waveguide gratings, for precise wavelength management with tight spacing. This diagram shows the basic operation. The MUX combines various wavelength channels onto a single optical fiber. At the other end, the DMUX separates these wavelengths back into their individual streams. Modern DWDM systems use sophisticated optical technologies for enhanced precision. This includes fiber Bragg gratings, which reflect specific wavelengths, and arrayed waveguide gratings, which are used for high-channel multiplexing and demultiplexing. Thin film filters, TFF. Filters specific wavelengths. Diffraction grating separates light into spectral components. Diffraction gratings rely on diffraction to split polychromatic light into its spectral components at different angles. Thin film filters use interference films that pass only a specific wavelength while reflecting all others. Arrayed waveguide gratings, or AWGs, utilize interference within precise waveguide structures. This allows them to separate many channels, which is a common and necessary capability in DWDM systems. DWDM MUX features include a passive nature, meaning most units are unpowered. They use optical filters like thin film filters or athermal arrayed waveguide gratings to combine and split light without electricity. A key feature is protocol independence. The DWDM technology is transparent to data, allowing it to carry various traffic types like Ethernet, SONET, SDH, and fiber channel simultaneously and at different speeds. DWDM MUX DEMUX modules include specialized ports for enhanced flexibility. The common line port is the main fiber connection where all multiplex signals enter or exit the device. The expansion port allows for cascading additional units to increase the total number of channels. The monitor port taps off a small percentage of the signal for real-time performance monitoring without interrupting traffic. The 1310 nanometers port is a wideband port that integrates legacy 1310 nanometer signals alongside the DWDM channels, supporting existing infrastructure. Thank you for watching this video. Please subscribe to the channel for more updates and information.